So we ended talking about divisibility. So where were we going with that? Well, we talked briefly about factors. So if we're looking at factoring something or looking at factors of 141. If I want to list off factors, I can kind of go right down the list. Is it divisible by 2? No. 3. 1 plus 4 is 5 plus 1 is 6. It is divisible by 3. Divisible by 4? Oh, yeah, 41 is definitely not divisible by 4. 5? No. 6? No, because it's not even. 7, we'd have to check. But if you tried it out, if you tried to divide by 7, we'd get 20.142857143 approximately. Obviously not divisible by 7. 8. Well, if it's not divisible by 2, it cannot be divisible by 8. Now it's divisible by 3, so 9 is a possibility. Can we divide it by 9? No. I'm not even going to ask any more even numbers like 10, 12, 14, 16, because if it's not divisible by 2, it cannot be divided by any other even number. 10? No. 11? No. 13? No. 15? Nope, it doesn't end in 5. Right? 15 is divisible by 5, so it has to be divided by 5. 17? No. I'm going to make it easier on us. If we know it's divisible by 3, let's divide it by 3. We get 47. We know it's divisible by 47. Can 47 be divided by anything else? No. 47 is prime. 141 can be divided by 3 and 47. Those are its only factors. How about we try 258? Can it be divided by 2? Yes. 3? Yes. 4? 4, no. Can't be divided by 4. No. Yeah, 58 can be divided by 2, it'd be 29, but it can't be divided by 2 again. 5? Nope. 6. It's divisible by 2 and 3, so we know it's divisible by 6. 7? No. 259 would be divisible by 7, but not 258. Again, the only way to check is to divide it. 8. No, it's not quite divisible by 8. 9? Nope, adds up to, the digits add up to 15, which is not divisible by 9. 10's obviously a no. 11? Nope. It's divisible by 2 and 3, but it's not divisible by 4. If it was divisible by 12, it would have to be divisible by 4, because 4 is a factor of 12. How about 13? Nope. So we can keep going with this list if we want to. We don't have divisibility rules higher than that. So let's stop there. But I'm going to do this. One way to find factors is to split it up. We know that it was divisible by 2. So if I divide it by 2, I'm going to get 129. 2 is prime. It can't be split up anymore. 129, however, can be divided by 3, which is going to give us 43. Can 43 be divided anymore? No, it cannot. 43 is prime. So what I have here is I have the 2, the 3, the 6. 43 is going to be a factor of it. Is there anything smaller than 43? No, there isn't. There's 43, there's going to be 86, and there's going to be 129. 120, where did I get the 86 and the 129? 258 divided by 3 is 86. 258 divided by 2 is 129. 258 divided by 6 is the 43. So for every one of these smaller factors, there's got to be a larger one as well. So anyway, what we just did here is what we call a factor tree. And when we look at these, there's all sorts of factor pairs of 258. We just saw 3 of them. 2 times 129 would be a factor pair. 3 times 86. 6 times 43. The question is, which one do we want? If I ask you to factor 258, what pair would I want you to have? Well, because of that idea that there's several possibilities, we usually don't just ask for factor pairs. We ask for what is called prime factoring. Prime factoring is where we take the number and we reduce it down to the smallest prime numbers we can multiply together to get that number. For example, if I ask you to factor 360, prime factor 360 to be more specific. Now remember, I said that when I look at dividing numbers, I look at 10, 5, 2, and then 3. Can this be divided by 10? Yes, it can. If I divide it by 10, what's left over? 36. That's the second reason why I look for 10 first, because it's really easy to divide by 10. You just take the 0 off. Now, the 10 can be split up into what? 2 times 5 or 5 times 2. Both of those are prime. They cannot be split anymore. 36 can be divided by 2, which would leave me with 18. Or 6 and 6 would have worked as well. Now the 2 is prime, so I circled it. 18 can be divided by 3, which would leave me with 6. 6 can be divided by 2, and which would leave me with 3. Now I circle everything when it gets to be a prime number, so I know I don't have to divide anymore. So what I have here, and I usually write them in order from smallest to largest, I have a 2, and another 2. 2 times 2 times 2. I have a 3 and another 3, times 3 times 3, and a 5 times 5. So 360 prime factored is 2 times 2 times 2 times 3 times 3 times 5. Or, this is why I did the powers and stuff at the beginning of the last hour. I could write it as 2 to the 3rd power times 3 to the 2nd power times 5. Either one of those is a totally acceptable answer. Now your book might ask for it, or my math lab might ask for it in exponential form. That's exponential form with exponents. So we could factor 450. So what's something that goes into 450? 45. So 10 and 45. Good. Can 10 be split up? 2 times 5. 2, of course, is prime. 5 is prime. Circle it. 45. 5 and 9. Good. We see it ends in 5, so we know it's divisible by 5. 5 is prime. How about 9? Split into 3 times 3. So again, I'm going to write this as 2 times 3 times 3 times 5 times 5. I could leave it like that, or I could do 2 times 3 to the 2nd times 5 to the 2nd. So 2 times 3 squared times 5 squared. Again, either one of those is an acceptable factor. In your notes, I'm going to have you factor 196. So 196 can be divided by 2 and 98, okay? 2 is prime. 98. 2 and 49. 2 is prime. 49, is that prime? No. 7 and 7. So 96 is 2 times 2 times 7 times 7, or 2 squared times 7 squared. Either one. How many of you had that? One of those two. Cool. One more for you to try. 306. Prime factor that one quick. So if we look at it, not divisible by 10, not divisible by 5, but it could be divisible by either 2 or 3. Which one did you guys see first? 2, okay, so divided by 2 would give us 153. 2 is prime. 153. 3 and 51, very good. 51. 3 and 17, very good. So this is 2 times 3 times 3 times 17, or 2 times 3 squared times 17. Why on earth am I spending this time doing factor trees? Why does it matter? It's not just a way of me torturing you guys. That's just an added bonus. Why is a factor tree so important? Well, because there are two concepts that we look at in math that are very common concepts that come up a lot. And when we're dealing with numbers, with whole numbers, we tend to just do them in our head and not really think about where they're coming from. But when we get into algebra and we have variables and stuff involved, the factoring is the process we need to go through to find them. And so if we do them with the numbers, when we get to the variables in the algebra, the algebraic numbers, we know what to do to find these things. The first one is something called a greatest common factor. From here on out to be known as the GCF. Certain numbers have factors in common. If I were to put up 18 and 24, they have a lot of factors in common. Both of them have factors of 2, 3, 6. The greatest common factor is saying, look at all those common factors and find the largest one. Now, I could list out all the factors of each of them and find the biggest one, but that might be a lot of work. But if we prime factor each number, and I'm going to assume you can do the factor tree right now. 18 would be 2 times 3 times 3, if I did the factor tree. 24 would be 2 times 2 times 2 times 3. The greatest common factor is a combination of all the common factors. What do they have in common? They have a 2 in common, and they have a 3 in common. What's 2 times 3? 6. 6 is the greatest common factor of 18 and 24. What if I asked you for, oops, that's not going to work, just a second. The greatest common factor of 84 and 210. This might require a little more work. 84, well, I'm going to go like 4 and 21. 4 can split up into 2 and 2. Those are prime. 21, 3 and 7. So this is 2 times 2 times 3 times 7, because it's factors. Notice I'm not using the exponential form. I'm writing out the individual factors, because it's easier that way when I'm looking for the greatest common factor. 210. Well, looks like there's a 10 and a 21. 10 is 2 times 5. 21 is 3 times 7. So it looks like I have 2 times 3 times 5 times 7. What do they have in common? A 2, a 3, and a 7. 2 times 3 times 7 is 42. 42 is the greatest common factor. I'm going to have you guys try to find the greatest common factor of 88 and 154. So if I prime factor 88, what do I get? 2 times 2 times 2 times 11. Good. 154? 2 times 7 times 11. There we go. What do they have in common? 2 and 11. 2 times 11 is 22. So 22 is the greatest common factor. You wrote your 7 so it looked like a 2, didn't you? Yeah. I do that too. Don't worry about it. The other process is something called a least common multiple. From here on out to be known as the LCM. The least common multiple. A multiple is a number that number divides into. For example, multiples of 7 would be 14, 21, 28, 35, and so on, because all of these numbers can be divided by 7. The least common multiple, if I have two numbers of like 12 and 16, is the smallest number that both of those can go into. Now for 12 and 16, it would be 48. How do I use my factors to accomplish that? Well, 12 and 16, if I factor them, 12 is 2 times 2 times 3. 16, 2 times 2 times 2 times 2. Again, I'm assuming you guys can do the prime factor trees. Now, what I'm going to look at, I'm only going to look at what they have in common just so I don't repeat them. They already both have a 2. They already both have a second 2. This one has a 3 that the other one doesn't. So this one needs, I'm going to put it in red. This one needs a 3. Now they both have a 3. This one has 2 2s extra. This one needs 2 more 2s. Now they both have the same number of 2s. Do you see what I did? I made sure they all had the same factors. This now multiplies up to 48. This now multiplies up to 48. The least common multiple is 48. Let me do some more examples of that. Let's look at 6 and 18. If I factor 6, I get 2 times 3. If I factor 18, I get 2 times 3 times 3. If I look at what they have in common, they both have a 2, they both have a 3. Right now, the only extra thing sitting there is the 3. Where do I need to put that? On the 6. 2 times 3 times 3 is 6. 6. 2 times 3 times 3 is 18. 2 times 3 times 3 is 18. 18 is the least common multiple. It is okay for one of the numbers to be the least common multiple. Let me find a more complicated one here. Let's look at like 42 and 30. So if I factor 42 and 30, 42 is 2 times 3 times 7. 30 is 2 times 3 times 5. They both have a 2, both have a 3. Again, what we're concerned with is what's left over after we look at the common pieces. This one has a 7, so this one needs a 7. This one has a 5, this one needs a 5. Now, do they all have the same factors? Yes. This multiplies up to 210. This multiplies up to 210. 210 is the least common multiple. We can work with more than 2 numbers. We can do 8, 6, and let's do 4. So same thing, I'm going to factor each. 8 is 2 times 2 times 2. 6 is 2 times 3. 4 is 2 times 2. So if I look at what they have in common, they all have a 2. Well, this one has 2 2s, doesn't it? The 6 doesn't have any, so I need to give this 2 more 2s. This has 2 2s. The 4 already has 1, so it only needs 1 more. So now each of them have 3 2s. This one has a 3, the other ones don't, so they need 3s. So now I have 24, 24, and 24. That's how you double check, is to make sure they all multiply up to be the same thing. I'm going to show you an alternative way of looking at this quick. We had talked about writing these things out in exponential notation. This is 2 to the 3rd power. This is just 2 times 3. There's no power. This is 2 squared. The alternative way of looking at it is you look at each factor. What factors are involved here? There's 2's and there are 3's. What is the highest power on the 2? 3. Highest power on the 3? Oh, just the 1. Just the 3 by itself, right? So 2 to the 3rd power, 2 times 2 times 2 times 3 is 24. It's a little bit simpler if you do it. A lot of people, some people don't like the exponential form. So let me do, let's see here, 70, 45, and 28. If I factor 70, it is 2 times 5 times 7. 45. 3 squared times 5. 3 times 3 times 5. Right? 28 is 2 squared times 7. So I look at all the factors I have here. I have 2's, 3's, 5's, and 7's. Highest power on the 2, squared. The 3, squared. The 5, just the 1, no power. The 7, just the 1, no power. So 2 times 2 times 3 times 3 times 5 times 7 is 1,260, I believe. So 1,260 is the least common multiple. Still not necessarily easy, but like I said, some people find the exponential form easier than the other. So why is it that greatest common factors and least common multiples mean anything to us? Well, because the next topic we're going to cover uses both of them. Everybody's favorite type of number, the fraction. I know, I'm being sarcastic. The top there was the numerator. We said that was a count. It's telling us how many of something we have. We have 3 of something here. Just like we could have 3 inches or 3 cows or 3 pounds. The 4 is a name. It's telling us what we have. It's not a number, it's a name. Just like cows or inches. So the first step we have to take to deal with fractions and understand fractions is to understand what it means to be a fourth. Well, the simplest way to deal with that or illustrate that is to go back to the old elementary school illustration. Pretend that looks like a circle. of a pie or a pizza or however you want to look at it. Fourth means that's cut into 4 equal pieces. Pretend those look equal. So either each whole object is cut into 4 equal pieces, or it takes 4 of those pieces to make one whole object. You can look at it either way. 3/4 then means that out of those 4 pieces, we have 4 of them. Now, we encountered back on the first day of class, we talked about trying to add fractions and how they have to have the same name. And we looked at an example where they had different names and we couldn't add them. So one of the first things we're going to need to do is figure out how to rename a fraction. One of the simplest things we can do is off this illustration, we can just take each slice of pizza here and cut it into equal slices. So I'm going to cut each into 3 equal slices. Again, pretend these are equal. Close enough. Now, how many pieces does it take to make one whole object? There's 12 of them. We had 4 pieces before. We cut each into 3 equal pieces. 4 times 3 is 12. How many pieces do we have in yellow now? 9 of them. We had 3 before. We cut each into 3 equal pieces. 3 times 3 is 9. So now what we have is 9 twelfths. Do we have any more or less than we did before? No. 3/4 and 9 twelfths have exactly the same value. They just look different. Why is that? Well, what we did here, we multiplied by 3/3. The bottom 3 says it takes 3 pieces to make a whole object. The top 3 says we have 3 of them. In other words, we have one whole object. We just multiplied by 1. And when we multiply by 1, what does it do to the value of a number? Nothing. It stays exactly the same. This is what we call a unity fraction. It is a tool that we use in math a lot. Not all of them are as obvious as this one, but when we go to do measurement conversions and stuff like that as well, we use unity fractions to convert our measurements, convert our units. It'll always change the appearance, but not the value. So the first thing that we need to determine whenever we're doing this is what name we want to change it to. So let's say we have 2/5 and I want to change it to 30/5. The second thing we need to determine is what we have to multiply the 5 by to turn it into 35. And in this case, it would be 7. 5 times 7 is 35. So now we do 2 times 7 to get 14. Again, 14 35ths has exactly the same value as 2/5. So if I have 1/3 and I want to change it into 36, what's this going to become up here? 12. Because 3 times 12 is 36. I have to do the 1 times 12 to get 12. 12 36 and 1/3 have exactly the same value. So in your notes, 5/7 becomes how many 28ths? What'd you get? 20. 7 times 4 makes 28. 5 times 4 makes 20. 20 28ths has the same value as 5/7. We can go the other direction. We could have something like 48/60. This means it takes 60 pieces to make a whole object, and we have 48 of them. Trying to visualize that is really difficult. Actually, the average human brain can visualize between 7 and 13 things before they lose track of them. But we can reduce this. We can simplify it. We can reverse this process up here. If I had the 20/28, I multiplied by 4 on top and bottom with the 5/7 to get that. I could divide by 4 on top and bottom to get back to 5/7. So I have to look at this here, 48/60, and I have to figure out what both of those can be divided by. They can be divided by 12, which would give me 4. 48 divided by 12 is 4. 60 divided by 12 is 5. 4/5 has exactly the same value as 48/60 is. They just look different. Now the 12 is a greatest common factor of 48 and 60. So we could do that factoring that we did to find that greatest common factor. Now, realistically, we don't have to. We've always been told that you had to find that greatest common factor and divide by that largest number to reduce a fraction. Realistically, we don't. I could look at these and say, hey, both of those are divisible by 2. I can see that really easily. 48 divided by 2 is 24. 60 divided by 2 is 30. Now that it's 24 over 30, it might be easier to see what else it can be divided by. Now it's a lot easier for me to see that both of those are divisible by 6. But even if not, I could see that they're still divisible by 2, which would be 12 over 15. And those are both divisible by 3, giving me 4 over 5. So I don't have to find that greatest common factor. It makes things a little quicker if I do. But all I really have to find is any common factor and divide. And then see if there's any more that I can divide by. So if I want to reduce 42 over 56, what can both of those be divided by? Well, 10, no. 5, no. 2 would give me 21. Divided by 2 would give me 21 over 28. Is there anything else? 7. Very good. 21 divided by 7 is 3. 28 divided by 7 is 4. How about 45 over 120? Can both those be divided by? 5, right? 45 divided by 5? 9. 12, or 120 divided by 5. 24. All done? No. Both divided by 3. 9 divided by 3? 3. 24 divided by 3? 8. 3/8. Perfect. Any questions? Another thing we can run into is something like this. 44 over 7. The 7 is telling us it takes 7 pieces to make a whole object. The 44 says we have 44 pieces. We have enough pieces to make not just one, but several whole objects. So it'd be easier if we split them up so that we had the whole objects with pieces left over. What we have right here, this is what's called an improper fraction. There's an improper implies there's something wrong with it, and there isn't. There are times when we really prefer it to be in this form. But we don't like having the numerator bigger than the denominator, so they call it improper fraction. We're going to change it into a mixed number. A mixed number is just that. It's a mixture of whole objects and then the fractional pieces that are left over. So we need to first figure out how many whole objects we can get out of that. We would do 44 divided by 7, which would give us something like 6.2857143 approximately. What's that tell us? Other than I have too much text to type. Yeah, there's 6 whole objects and there's a remainder. There's pieces left over. So this is 6 whole objects. How many pieces were used up by the 6 whole objects? Yeah, 6 times 7 is 42. So how many are left? 2. So there's 2 7s left. Basically, what this is a long division with a remainder. 44 over 7 becomes 44 divided by 7. 7 goes into 44 6 times. 6 times 7 is 42. There's 2 left over. So there's 2 7s left over. 6 and 2 7s. So what if I had 48/5? Many of you can probably do this in your head. I'm going to write it out. 5 goes into 48 9 times. 9 times 5 is 45, so there are 3 left over. So 9 3/5. 23 thirds. Three goes into 23, 7 times. 7 times 3 is 21. There's 2 left over. So it's 7 and 2 thirds. Let's have you try. Reduce. 36 over 84, and I'm going to have you reduce 51/8. So 36 and 84 can both be divided by, well, I see a 2, they're both even. That gives me 18 over 42. Anything else? 6. Otherwise, I can still see they're divisible by 2 if I wanted to. That would work as well. 18 divided by 6 is 3. 42 divided by 6, 7. 3 sevens. How many of you got 3 sevens for that one? Good deal. 51 divided by, or 51 over 8. I'm going to set it up as 51 divided by 8. How many times does 8 go into 51? Well, 6 times 8 is 48. I'll leave me with 3. So 6 and 3/8. How many got 6 and 3/8 for that one? Good deal. Sometimes we want to be able to go the other direction. Sometimes it's beneficial to take this mixed number, like 3 3/4, and turn it back into an improper fraction. To do that, we have to take this whole number, the 3 whole objects, and bust it into pieces. Well, the denominator tells us how many pieces each of those is going to become. This is fourths, so each whole object is going to become 4 pieces. So 3 times 4 makes 12 pieces. So do we have 12 pieces now? We still had 3 before, right? So 3 plus 12 is 15 fourths. So if I have 5 and 1/3, what I'm doing is I'm taking my 5 here, my whole number, times the denominator to give me how many pieces the whole number is. So 5 times 3 is 15, plus the 1 that was already there is 16 thirds. So 7 and 3/8. 7 times 8 is 56 pieces from the 7. 56 plus 3 is 59 over 8. Two and 5/11 will become 27 over 11. 2 times 11 is 22, plus 5 is 27. Perfect. So let's have you convert 5 and 5/7 to a mixed number. And I'm also going to have you convert 3/4 into 20/4. So 5 and 5/7. 5 times 7 is 35 plus 5 is 40. So 47. Good. 3/4 into 24. Well, 4 times what is 24? 6. So I have to do 3 times 6 to get 18. 18 24s. Beautiful. Okay, so there is a new quiz that is due tomorrow, Friday, at 11:59 p.m. There is a new homework that is due for class next Tuesday. We did not get time to cover circle graphs. There's a couple of those in the homework. If you can't figure them out, we'll start out next week or next Tuesday discussing those. Y'all have a great night. Have a great weekend. Those of you here in Rice Lake, the computer lab next door is open and operational if you want to get started on the quiz or the homework. I did leave you a whole 4 minutes to work on it.